So in this lecture we continue with our discussion on MOSFET, and this slide shows basically that we have a dependence of current ID which flows in the transistor. It has a dependence on W, which is the of course the width of the transistor. So normally the current is quoted as milliampere per micrometer of width. Okay, so this is one way to express the current as a function of the width. So now here is our first parameter. Okay, so the first parameter for our transistor is the on current, or I on, which is basically the current that flows in a transistor when you apply a voltage at the gate that is enough to turn the transistor on. Okay, we have already seen the output characteristic curve of a transistor, that is VDS and IDS curve. Okay, at a fixed VGS. So we have seen this characteristic curve, which is called the output characteristic curve, and the I on is basically equal to the current that flows in the drain at a condition. And what is that condition? The condition is this one, that when the gate is at a voltage that is equal to VDS and that is equal to VDD. So as VDD is large enough to turn the transistor on, so we have this characteristic curve. So this is the on current, and as we talked in the previous slide, it is expressed in microampere per micrometer or milliampere per millimeter. So this is the width dimension of the transistor. Now this on current is basically very important because it determines the speed of a digital circuit. Okay, so basically the time for a digital circuit to switch from positive to negative, or from 0 to 1 or 1 to 0, is determined by this formula, which is tau, or speed of the circuit, is proportional to what is CSW. It is the switching capacitance. Okay, it is the switching capacitance. VDD is the applied voltage, and I on is the current that flows in a on transistor. Okay, and basically this V by I is R. So you can say this circuit speed is basically a function of the RC. So this is called RC time constant. You may have seen the RC time constant and its significance in other courses. So it has a very important role in determining the speed of a digital circuit, and we will talk in a great deal of detail in upcoming lectures on delay. So we will come to delay, and we will have detailed explanation of how the circuit speeds and how we can calculate it. Now the second parameter for a digital circuit is the off current. So sometimes we denote it as I off, and I off is basically the current when the gate voltage is 0. So basically in this condition the transistor is off. So ideally the current here should be 0. So I off ideally should be 0. Okay, but in reality it is not the case. In reality there is a significant amount of current, and why I said significant, because with the scaling of transistors, so as we are moving towards smaller and smaller transistors, the I off current is not equal to 0. Okay, so this is reality, and so this is ideal, and this is what reality is. Okay, so you saw this was the characteristic which we call transfer characteristics, because on this input, on this axis we have an input which is VGS, and on this axis we have our output which is ID. So the current is almost 0 beyond a threshold, before the threshold voltage, and beyond the threshold voltage it increases exponentially. So this region is also called the subthreshold region. Okay, now again, as I told you that I off is not equal to 0, so this is another plot which shows the ID in a logarithmic plot. Okay, and you may know that logarithms are well suited if you want to express very large quantities or very small quantities. So it is ideal for plotting very large or very small quantities. As the I off current is very small, that's why it is plotted on a logarithmic scale. And when you plot it on a logarithmic scale, the plot looks something like this. So you have this, you see, a finite, we have a finite value, finite non-zero value for I off. Okay, so although that VGS is 0 and there should be no current, but still some current flows because you see the transistor is not ideal, and the physical manufacturing of all the PN junctions and all these things, they dictate that a very small amount of current flows even in the off state. And this off current is basically very important these days, because the static power of a chip, okay, of a chip or any device is basically determined by the I off current. So Ng is your number of gates. So even if you have a very small I off, but as Ng is very large, okay, what happens is that the product of I off and Ng, it becomes significant. And that's the reason that in the latest technology, the static power is on the rise. Okay, the static power is on the rise. What that means? That means that ideally, if your transistor is off, it should not consume any power. But due to the this factor Ng cross I off, which is significant, even in the off state, if your circuit, if your transistors are off, so imagine you have like 1 million transistors, and for example, only 500,000 transistors are switching, but the other 500,000 are off. Okay, so ideally those off transistors should not consume any power, but because of this formula, they consume what is called static power. So there are two kinds of power consumption. We will go into great detail into power consumption after we discuss delay in the upcoming chapters and lectures. So there are basically two kinds of power consumption. One is static and the other is dynamic power consumption. The static is what we discussed, and the dynamic power consumption is basically, it is the power consumption that is due to switching. So when the transistor moves from 0 to 1 or 1 to 0, that we call switching. So it is due to switching. So that is okay. So we come to the third important parameter, and the third important parameter is what is called subthreshold swing. So the definition of subthreshold swing is that it is the change in VGS per decade, which means per 10x change in ID. So that is the definition of subthreshold swing. You see, subthreshold is the region that is on the left side of threshold voltage. So we are talking about that region, and it is expressed usually in millivolt per decade. So this is another important parameter. And why this is important? This is important because it has an effect on the I of current. So a higher subthreshold swing, if this is high, it implies that I of is also high. Okay, and that is bad. We don't want I of to be high. Okay, so if your transistor has a characteristic curve where the subthreshold swing is high, then it will have a higher of current. For example, here we have two curves. One is this dotted curve, okay, which has a SS value that is lower than the other one, which has a higher, SS2 has a higher value. What effect it has is that the I of 2 is also greater than I of 1. Okay, and we do not want I of to be greater, because if I of is greater, this what this implies is that your static power is also increased. Okay, so it means that your static power has also increased. So again, this is the same slide. We discussed this formula, the first one. Okay, this is the formula for the static power, and it is proportional to NGI off and the supply voltage. And we will discuss this one. This is the formula for dynamic power consumption in greater detail in the upcoming chapters. But you can see that the dynamic power is determined by this alpha, which is called switching activity factor. Switching activity factor means how many transistors that are in your circuit they switch at a time. So if more transistors are switching from 0 to 1 or 1 to 0, then the power consumption will be higher compared to if less number of transistors are switching. The next thing is the frequency of operation. So for example, if you have a chip that is running at 1 GHz and another chip that is running at 3 GHz, the one running at 3 GHz will consume more power. And we already talked about this one, which is the switching capacitance. So interestingly, you can see that the dynamic power is proportional to the square of voltage, the square of your power supply. So if you want to reduce the dynamic power, and obviously we want to reduce the dynamic power and static power also. Why? Because we want that, for example, our laptops, they should run for large amount of time on a single battery. So if we want to save the battery, we want the static and dynamic power consumption to be as small as possible. Okay. So this formula tells us if you want to reduce the dynamic power, you have to reduce the frequency, you have to reduce the switching activity, you have to reduce the capacitance, and you have to reduce the voltage, supply voltage. And when we come back to the power consumption chapter, we will see how we can deal with these different kinds of factors to control the dynamic power. So static power is controlled by the off current. It is also determined by the sub-threshold swing. And to minimize the dynamic power, you have to either control the frequency or power supply or the switching activity or the capacitance. We will see some of these factors can be controlled easily, some cannot be controlled. So we will come back to this. Okay. Reducing VT also increases the I of current. So what that means, so let's come to the last point, which is this sub-threshold swing determines the minimum power supply voltage. What that means? In order to explain this, let's go to the slide. So you see that the dynamic power, okay, it was proportional to VDD square. So if you want to really control the dynamic power, you should decrease this. Okay, and the power consumption, dynamic power consumption, will reduce as a square, resultantly. So let's try to reduce VDD from VDD to VDD prime. Okay, and what that means is also that we are reducing the threshold voltage from Vt to Vt prime. Okay, so now we have a lower threshold voltage to turn the transistor on. Okay, so what will happen as a result, that our Vt, which was here, okay, it has moved to here. Okay, so our curve has also moved. So the dotted curve was our original curve, and the bold curve is our new curve. So it has been shifted, which, as we saw earlier, that if this is our SS1 and this is our SS2, so the SS2 is greater than SS1, which also means that I of 2 is greater than I of 1. So what that means, we started with the goal to reduce the dynamic power, okay, but in the process we have triggered a scenario in which the static power will go up, because our subthreshold swing and the I of current are changing. So what this means is that the subthreshold swing is a very important parameter, and it puts a limit on how much you can reduce your supply voltage. Okay, so this slide summarizes the things that I told you. So SS must be minimized to minimize I off, SS must be minimized to minimize VDD. Okay, but this SS basically is a property of the MOSFET, and it comes from how you construct the MOSFET. So it is like a fundamental limit, and you see that for some of the MOSFET, the SS should be greater than 60 millivolt per decade at a temperature of 300 Kelvin. Okay? So this limit comes from how the transistors are manufactured. You cannot reduce the subthreshold swing below 60 millivolt per decade. Now let's come to the effect of drain voltage, VT. What happens with the drain voltage and how it affects the current ID? So the answer is in several different ways. It affects the physical underlying behaviors of the transistors. So you see that the ideal transistor should be something like that you have a linear region and then you have a saturation region. We already talked about this, that in the linear region it acts as a resistor, and in this region it acts as a current source. But actually the curve is not like this, but it's more like this. It has this saturation region which has a slope. It has a finite slope, and we talked about this in the first part, that the slope is due to a resistor kind of behavior. Okay, so in the linear region you see that ID is proportional, linearly proportional to VDS, but in the saturation region the relationship is not what is, you can say, it's not ideal. Okay, and we will go into more detail about the kinds of effects. So if we talk about the saturation region, there is a resistor, okay, there is intrinsic output resistor, intrinsic have an infinite output resistor. So this is for the case for ideal MOSFET. Real MOSFET have this finite resistance R0, and as I told you, the R0 is basically the slope of the curve here. So it is the slope of the curve here. See, whenever you take the differential of something, that differential gives you the slope. So that is a non-ideal behavior. R0 is a non-ideal behavior. Ideally, it should be 0, but in reality, R0 has a finite value. What this means is that when you are in saturation region, okay, the saturation region, then if you increase VDS, okay, ID will increase. So this is non-ideal. Okay, this is non-ideal behavior. What was the ideal behavior? The ideal behavior was that ID should increase only by a change in the gate voltage, because our transistor is a gate controlled current source. So that was the ideal behavior. But due to this non-ideal behavior, due to this finite output resistance, we have this condition that by increasing VDS, the current will increase. So again, this is the slide that explains it with another picture. So you see, it is the plot of VGS versus ID, and here VDS is 0.05 volt, and here VDS is VDD. So you see, there is a huge difference between how the current changes. So in one case, VDS is low, the current changes slowly, and in the other case, it changes very, very fast. Okay, then we have another effect. So first, let me explain what DIBL means. DIBL means drain induced barrier lowering. So DIBL. So that is the abbreviation of DIBL, but the definition is basically this one, that DIBL is the change in gate voltage per change in drain voltage. The condition is this one, that this should happen at same, so ID is fixed, it is the same. And another important thing is that DIBL is in the subthreshold region. Okay, so it's not in the linear region or in the saturation region. DIBL is in the subthreshold region. And if we come to the curves, so here we have VDS equal to, let's say this is VDS1, and this is VDS2, which is equal to VDD. Okay, then you see that the VGS also changes. So it goes from VT saturation to VT linear. Okay, but you see that the current ID should be fixed if you want to measure DIPL. So the unit of DIPL is millivolt per volt. Okay, and so we will come back to this DIPL when we explain and discuss the internal functionalities of how the charges move with applied voltages and all that. So we will discuss and we will know why this is called barrier lower. So we will come to this in the upcoming lecture. So the drain non-ideally on idealities include DIBL, which we discussed, the infinite output resistance and the threshold voltage dependence. All of these we have discussed. Okay, and these are related to DIBL. So again, this is the formula for DIBL. It is basically the change in VGS by the change in VDS at a fixed voltage. So the higher the DIBL, if DIBL is higher, it means the more sensitive threshold voltage is to drain voltage. Okay, so we can say sensitivity of VT also increases, and this also implies that the output resistance is low. So ideally the output resistance should be infinite, but if DIBL is higher, it will mean that R0 is low. So this is the summary of the lecture on the figure of merits for digital application. We discussed the on current, we discussed the off current, we discussed the sub-threshold swing, and we discussed DIBL and what implications they have.